Alright, here we go with a nice example. This is a part of something we call reduction formulas, where you don't actually solve the problem per se in one shot, but you try to reduce it into something that's easier and hopefully establish a pattern that can be reused over and over again to keep making it simpler and simpler and keep getting closer and closer to the ultimate solution. Again, maybe I should write it down here. This is called a let's call it a reduction formula. Reduction formula, right? This is part of a bigger family. So let's see how it goes. We're going to try our luck using certain u value. We're going to make u. What should I make my u? I'm going to try with u is equal to x squared plus 1 raised to the negative 20. That's the bottom part. Whatever is left over is forced to be my dv. dv would be equal to dx. Complete the dictionary by differentiating this way and integrating this way. We differentiate, so du would be equal to negative 20 times x squared plus 1 raised to negative 21 times 2x times dx, the derivative of the stuff inside. On this way, we go the other way, integrate both sides. Integral of v dv integral of dx gives you v must be equal to x. Piece of cake. Alright, we write our bipart statement. Where did a bipart statement go? You've seen it already. Alright, so this will become integral of dx over x squared plus 1 raised to the 20th is equal to vu. That would become x times x squared plus 1 raised to the negative 20 minus integral of v du. So it would be x times 20 times x squared plus 1 to the negative 21 times 2x times dx. This whole thing is v du. Okay? That would become, I clean this up a little bit, and this would become integral of dx over x squared plus 1 raised to the 20th, and that's equal to x over x squared, no, not x squared, I meant x squared plus 1 raised to the 20th minus, let me see if we can clean this up. Here I see a 20, here I see a 2, here I see an x. Alright, let me see if I can pull out a 20 times 2 times integral x squared dx over x squared plus 1 raised to the 21. Okay, how do you like that? Take a little break and relax. Enjoy. Smell the flowers. Smell the U subs. Alright. Here's a famous trick. You've got an x squared here. On the bottom you got x squared plus 1, which is almost the same as the top except for the plus 1 there. If we had a plus 1, it'd be nice because we could reduce this easily. So one way to get a plus 1 there is just to put it on there. So we take a different color, say red, and let's go with I'm gonna subtract 1. Boom, you see I subtracted 1. We might wonder, how is that legal? Well, when you check numbers you can do that. You can just subtract 1 wherever you want. Not really. You should also add 1 here just to be fair. There. You can subtract 1 as long as you add 1, because that amounts to about 0, and so you really haven't changed the problem in a way that would make it unequal, but you've changed it in a way that's easier to work with. That would make this one be, let's go back to white here, so that would be the integral of dx, that would be over x squared plus 1 to the 20th is equal to x over x squared plus 1 to the 20th minus 20 times 2 integral of x squared minus 1 or plus 1 over x squared plus 1 to the 21st dx. And then I'd have a minus 1 there, so I'd have a minus, but then I have a minus minus. I think I have a plus integral of let me see here, plus 20 times 2 integral of 1 over x squared plus 1 raised to the 21st times dx. That's what happens when we distribute this. I had the plus 1. I should have made it here plus 1 minus 1. I don't know if it'll help. Yeah, maybe I should be more clear here. Take our little tiny baby eraser and make it perfect. Plus 1 minus 1. Alright, that way I separated the plus 1 there, the minus 1 there, but the minus and the minus had made it turn into a plus. That's why I got a plus there. Alright, everything good, right? Now what? Now we can clean this one up. See, I have 21 of them. I can make that 20, and that cancels one of them. And that turns into something that looks like this. The integral of dx over x squared plus 1 raised to the 20th is equal to x over x squared plus 1 raised to the 20th minus 20 times 2 integral of 1 over x squared plus 1 raised to the 20th dx. I know you might wonder right now, why is this crazy guy keep writing 20 times 2? Why not just write that as 40? Easy, because I'm not a pattern hider, you pattern hiders. Every time you simplify this, you hide the patterns, which is the last thing I want to do. I want to expose the pattern. It took me decades to learn this. You should never be simplifying stuff. You should always leave it unsimplified so you can expose the patterns. Unless, of course, you're into pattern hiding. If you want to hide all the patterns in the universe, go ahead and simplify. Whatever. Alright, let me continue here. So this simplifies, then I have plus, then I have 20 times 2 integral of 1 over x squared plus 1 raised to the 21st dx. And I think, man, this is getting worse. Because this is 21st. I started off with a problem that had 20 on them. Now I got even worse. And then right about now you would start to cry usually. Unless you have audacity and more audacity and you think nothing can stop us. Then we can proceed. Here's what we can do. This guy's had the same thing as the ones we started off with. This one has got the boomerang effect right here. Boomerang. I can move it over to the other side, collect it with this one, and see how it goes. If I move it over to the other side, I have that 1 plus 20 times 2 times the integral of dx over x squared plus 1 raised to the 20th is equal to x over x squared plus 1 raised to the 20th. That one got moved over, plus 20 times 2 integral 1 over x squared plus 1 raised to the 21 dx. Right? And then you might think, whoa, how is that going to help us? We're almost there. The thing is that if you really understand this pattern, you know that there's nothing special about the 20. Right? If that was if we had originally started with something like 500, it would have been easy to replicate this entire work to where, like, writing the answer this way, you should already know what the answer is. Here, talk is cheap. Let's do it. Alright, so we left off with that, and now we wonder, could we study that pattern and can we extract from it exactly what we need? What would happen if this wasn't a 20? For example, what would happen if this was a, I don't know, something like 300? So if we had started off with a problem that had dx over x squared plus 1 raised to the 300, can you see what the pattern would be? Where here you would probably have a 1 plus a 300 times 2. See, the power of not simplifying. If you had written 41 there, you would have had no clue where it came from. Writing it this way explains exactly where it came from and makes it easy to see the pattern here. This would have been x squared plus 1 raised to the 300. Plus this would have been 300 times 2. This would have been 1 over x squared plus 1 to the 301. And in this way we're getting more than just this problem. We're establishing the pattern for all of the problems that look like that. In particular, look at what would happen if this 20 was not a 20. But what if it was a 19? If it was a 19, it would look like this. It would look like the integral of dx all over x squared plus 1 raised to the 19th is equal to x over x squared plus 1 raised to the 19th. See the 20 become a 19, 19. Look at all the places where I'm going to put 19, 19, 19. This will be 19 plus 1. This will be 19. So I just go on and I fill in the pattern. This will be 19 times 2. Integral of 1 over x squared plus 1 raised to the 20th dx. And over here I'd have 1 plus 19 times 2. Right? That's what would happen if that was a 19. And that's exactly the one I want, because this is the one I was looking for, the one for 20. So all I've got to do is swing this over to the other side, and I would have solved for that. It would look like this. It would look like 19 times 2 integral of 1 over x squared plus 1 raised to the 20th dx is equal to, it's equal to that minus that, so it'll be negative x over x squared plus 1 raised to the 19th minus 1 plus 19 times 2 integral of dx over x squared plus 19, or x squared plus 1 to the 19th dx. That is just keeping this one on this side, moving this to the other side with a negative. That makes this one a plus, plus that. Okay? This is just algebra. Move this to the other side. Now I can see the pattern. Wait, I can divide both sides by that still, so I get that integral of 1 over x squared plus 1 raised to the 20th dx is equal to 1 over 19 times 2 times negative x all over x squared plus 1 raised to the 19th plus 1 plus 19 times 2 all over 19 times 2 times the integral of dx all over x squared plus 1 raised to the 19th. Duh, exactly what you would expect. There we go. What we've got is the original problem we wanted to solve in the reduction formula. See, this is to the 20th. Now we got it down to 19th. And conceivably, you could just repeat the same pattern. You wouldn't have to repeat the entire process, just repeat the pattern to solve that one. And you would probably get it down to an easier integral with 18 instead of 19. And just keep doing that a few times. After a couple of days, you'd be done with the problem. It's a beautiful thing. So here, I'll just do the next one for you. How would you do that? The direction pattern would go something like this. The integral of dx over x squared plus 1 to the 19th. That's that one. I'm going to play the same game here. It would be 1 over 18 times 2 times negative x all over x squared plus 1 to the 18th plus 1 plus 18 times 2 all over 18 times 2 integral of dx all over x squared plus 1 raised to the 18th. You wonder, well, how is that going to help us? Well, now you can solve that one. You just go 18 and the 17s, all of these ones, and on and on and on. That, my friends, is a famous thing. It's called reduction formulas. Very, very common using biparts. So it's a common way to get the problem into an easier version. We'll do another reduction formula next, where we integrate something like sine to the 20th power. And you'll see the gist of it. Very, very nice problems. Good chance to practice biparts skills. See you guys here next time. Peace.